going to very quickly describe the d orbitals because it's the same situation that's going to manifest. Okay, so dz squared, right? The z component, special for ml equals 0, we define as psi32 0, which is going to be made up of r32 and y20. And because there's no uncertainty situation with the z-axis, specifically the 3dz orbital will now be defined as psi320 star psi320. Brilliant. Then we'll have the dz squared orbital, which I'll show you a picture of here soon. So now, so remember, there's because L is equal to 2, there's 5 ml states, -2, -1, 0, +1, and +2. So we've taken care of the ml equal to 0, right? That's our z squared axis. So now we have 4 other ml states to consider, and all 4 of those ml states span either the y-z axis or the xz, or I should say plane, or the xy plane. And once again, because we're throwing all of our lot into the z-axis, we now have uncertainty situations to deal with for all 4 of these other ml numbers, -2, -1, +1, and +2. So let's do it, okay? So first, if we look at the +1, -1 state, we can make the d +1 and the d -1, just like we did with p, right? Where that's going to go, r32 y2 +1, that makes the d +1 state. And then the r32 y2 -1, that makes the d -1 state. A superposition is then created and then normalized. I'm not going to hold us responsible for doing that. I'm just going to give you the result directly. So the superposition now for the dyz wave function becomes 1 over I root 2 and d plus d minus. And then if we take the square modulus of that, we get the 3dyz orbital. And similarly, if we use another superposition, so it has a slightly different normalization constant and different permutation, 1 over root 2, d plus 1 minus d minus 1. That creates our superposition for the dzx, and if we take the square modulus of the dzx, we get the 3dzx orbital. Okay, great. So continuing along, so now if we look at the +2 -2 ml states, right? So ml plus or minus 2. So we've got the r32 y2 +2, and we'll call that the d +2. And we've got the r32 y2 -2. We'll call that the d -2. Fantastic. And in the same way, we get superpositions of either that will then correspond to the 3dx squared minus y squared or the 3dxy. And that comes, again, from this algebraic manipulation, f of r. So it's important to note this function f of r now does not equal, so for the d, does not equal the f of r function for p orbitals, right? But within the same block, or I should say the same subshell, within the same d subshell, that f of r function is the same for all of these. And so you can see through algebraic manipulation where those labels come from. The dxy is literally x times y times this function in r. Or, for example, the dx squared minus y squared is not quite identical to that, but it's close. It's 1/2 times the quantity x squared minus y squared times f of r. And the dz squared is a little funky, right? It's not like a pure z squared times f of r, but all the same, it still has that z squared, okay? So here's the picture of all those d orbitals that you all know and love from your Gen Chem days, okay? Oh, this one I just noticed says dx squared, but that is dz squared. That's a mistake in the textbook, haha. But what we're going to do, we're going to take this and put it in Mathematica. And what I always find really cool, as an undergrad, I always wanted to see all of these orbitals like put together on the same graph. And no one ever does that in textbooks for some reason. But here, we can easily do that in Mathematica. And that's what it looks like when we smash all 5 of those d orbitals together. And what I think is really cool when I think about this kind of shape, if I imagine like a transition metal, for example, that has a full D block. You know, we often, like when we draw pictures of those atoms, we just kind of draw them as little spheres, right? Like maybe if I had, you know, zinc atoms or something like that, right? I'd just have a bunch of neighboring zinc atoms as spheres, and you know, in an atomic lattice, right? They're all just going to be lined up. Well, when you look at all these orbitals together here, to me, I think a sphere is a pretty good approximation of this shape. It's crazy. It's got all these lobes sticking out. But as a gross approximation, if this were a full D block, right, everything is completely symmetrical about that point of origin, which is really neat. Okay, so let's see here. So the last thing, where are we going with this stuff? Yes, so I've been talking for quite a while, so I'll just try to wrap it up. If we now compare all of these different radial distributions, 1s, 2p, 2s, we can see the trend, and hopefully you remember this from Chem 109. And this is where we're going next is, you know, for the one electron atoms, or excuse me, what happens when now we have multi-electron atoms? What happens to this model? I also have a cool little Mathematica file I downloaded from the internet. It's called the Wolfram's Demonstration Project. So this is really cool. So they've got this whole manipulate feature, and they're plotting the radial wave function and the radial distribution wave function, and you can select through the different n and the different l's. So if we look at, so I'm going to go back now in my own Mathematica, right? When I made z is equal to 1 for 1s, that's the same function. Okay, this blue line here, if you remember our nomenclature, that gives us the expectation value, which if you remember for hydrogen 1s, that's about 72 or so picometers. So even though the most probable value is at the peak, the expectation value is right there. And it actually has to do with areas under the curve, right? The area under the curve to the left of that expectation value and the area under the curve to the right of that expectation value. Very cool. So now when I go up to n is equal to 2, this is a really cool model. So it goes to 2s. And so here you can see the radial profile for 2s. And then now you can also see those onion shells I was talking about, right? Those onion layers. So there's a node. The expectation value for 2s is, of course, out in that outermost lobe or layer, right? If we look at 3s, we get a similar situation. Okay, so there's the radial, and it shows 2 nodes. And now what's kind of cool is the expectation value for 3s is becoming much closer to the most probable value for that third lobe. And again, that just has to do with the areas under the curves. Okay. And then 4s, we see something similar, okay, which is very cool. But now what I can do is I can go back to this 2s, but I can now make it a 2p. All right. And so no more nodes. You can see that's where the expectation value is. I can look at 3p, and I see a similar situation. I can look at 3d, and right, remember, 3d won't have any radial nodes, so we see that there. And then finally, I could look at 4d, or I could even look at 4f, okay? And you would expect 4f to look really complicated, but it's not at all. And again, that's because of the way that radial nodes go as n minus 1 minus l. Okay, that's a pretty long lecture. Again, I know this was big stuff, so we should all take our time to digest this material. Okay, folks?